Okay, let's continue with the 9.1 video and discuss the different approaches to hypothesis testing. So in the textbook, there are three approaches to conduct a hypothesis test. The first is to calculate a Z or T test statistic and then compare it to a critical value or cutoff point. The second is to calculate the sample mean and compare it to a critical mean. And then the third is to calculate the p-value and compare it to the chosen alpha. So we will not cover the second method, so there won't be any examples or practice problems in this video. Now, a test statistic is a function of the sampled observations that provides a basis for testing a statistical hypothesis. In other words, we're going to use the sample data to calculate a test statistic and use it to draw an inference or decide on some business situation. So how do we make those decisions? So the purpose of a hypothesis test is to use sample information to decide whether to reject the null hypothesis about a population parameter. To do this, we need to select a cutoff point. Kind of like when you take a class as pass or fail, there's a particular cutoff point that will determine whether you pass the class. So in other words, we need to create a decision rule with a cutoff point. So for instance, right here is a decision rule if the sample mean is greater than some cutoff point in this region, we would reject the null. Or if it's not greater than the cutoff point, we do not reject the null in this region here. This would be the decision rule when we're working with a one-tailed upper tail test. The significance level is the maximum allowable probability of committing a type 1 statistical error. This is denoted by alpha, and in the previous video, we learned what type 1 errors are. These are false positives where we believe that the alternative hypothesis is true when it is not. So the decision maker of the test gets to choose the alpha or the significance level. This is based on how costly the error is in business. If making a type 1 error is very costly, we would want a small alpha value. If it's not very costly and we could afford to make the error, we would allow for a higher alpha value. So the chosen alpha has a corresponding cutoff point known as the critical value. So you can see the alpha is this shaded area that we're looking for, and the cutoff is where that alpha begins. This cutoff is known as the critical value and is the Z value or the T value based on the significance level that determines whether we reject the null. So we've talked about Z values and T values before in chapter 8, where the Z value is when we know the population standard deviation and the T value is when we don't. To conduct a hypothesis test for a population means, the method that we'll first learn is to calculate a Z test statistic and compare it to a critical value or a cutoff value. So when we know the population standard deviation, we will calculate a Z test statistic. This formula right here that you learned about in chapter 7. So as a refresher, we have the sampling error in the numerator and the standard error in the denominator. Once we find the Z test statistic, we will compare it to the critical Z value. On this slide, we will focus on how to use Excel to find the critical Z value when the population standard deviation is known. If you decide to use Appendix F for common alpha values, you will reference the infinity row in the last row of the table. The first thing we need to do is determine if we have a one-tailed or two-tailed test. Then, if we've determined it's a one-tailed test, then you need to decide if it's a lower or upper-tailed test. For a lower left-tailed test, we will use the function norm.s.inv function in Excel, and we will simply just input the alpha since we're interested in the region on the left side of the curve. So for example, to get the critical Z value for a 0.05 alpha, we will input equals norm.s.inv and 0.05, and we get a negative 1.645. The negative number is a sign that you did it correctly since we're on the left side of the curve. Now with an upper right-tailed test, this will be like the left-tailed test, but now we need to take the complement of 1 minus alpha. This is like when we were working with probability distributions when we were interested in the right side of the curve. So for the same 0.05 alpha example, we would use equals norm.s.inv and then 1 minus 0.05, and we get 1.645. So this makes sense since the alpha is the same, but now we're just looking at the right side of the curve. Now with a two-tailed test, since we have two tails, we need to split the alpha in half to get the critical value for either side. So for example, if we have an alpha of 0.01, we would use equals norm.s.inv and then 0.01 divided by 2, and we get a negative 2.5758. For a two-tailed test, we would use both the negative and positive value for the z critical value. Now, if the population standard deviation is not known, then we'll use the t-distribution to calculate the critical value. We also learned this formula in Chapter 7, where instead of using the population standard deviation in the standard error calculation, we replace it with the sample standard deviation. There are two key differences when calculating the t-critical value. The first is we need to calculate the degrees of freedom, or df, which is the sample size minus 1. Then for a two-tailed test, Excel has a specific function for two tails, which is t.inv.2t. We use this for the confidence interval calculation when the population standard deviation was not known. So here's an example for a lower left-tailed test. We will input equals t.inv and then the alpha of 0.05 and degrees of freedom of 15, and we get a negative 1.753. So the same as before, for an upper right tail test, we need to use 1 minus alpha, and we get 1.753. Finally, for a two-tailed test, we will use equals t.inv.2t and an alpha of 0.02 and a degrees of freedom of 22. It is important to note here, since the function is specific to a two-tailed test, you do not divide alpha by 2 like we did with the z critical value. And we get a plus or minus 2.5083. So let's work on a practice problem for finding the critical value. So in part A, the alternative hypothesis states that the population mean is greater than 13, and we're given a sample size, population standard deviation, and alpha value. So the first thing we want to do when we look at this is to identify if this is a one-tailed or two-tailed test. Since the alternative hypothesis states greater than, that means it's pointing to the upper tail of the distribution. So this is a one-tailed test. Next, since the population standard deviation was given, we know we'll be using the z critical value calculation from before. Also, since the alternative hypothesis is a one-tailed upper test, we know we'll need to use the complement rule for the alpha value. So we will input equals norm.s.inv and 1 minus 0.05, and we get 1.6449 or 1.645 rounded to 3 decimals. You can also validate this answer by referring to the appendix F and the infinity row, then across to the 0.05 one-tail column, and we could see 1.6449 at the bottom. So in part B, the alternative hypothesis states that the population mean does not equal 21. We are given the sample size, and in this problem, we are given the sample standard deviation denoted by S and the alpha value of 0.02. The same as before, we want to determine if this is a one or two-tailed test. So looking at the alternative hypothesis, we can see that this is a two-tailed test because the does not equal sign only applies to two-tailed tests. Since we do not know the population standard deviation, we also know from our examples on the prior slide that we'll be calculating the t-critical value. We will use the two-tailed function for the t-distribution and input equals t.inv.2t and 0.02 for the alpha and 22, which is sample size of 23 minus 1, and we get a negative 2.5083. And for the two-tailed test, we will use both the negative and positive critical value on both sides of the curve. So that's why we write it as a plus and minus 2.5083. So in part C, the alternative hypothesis states that the population mean does not equal to 35. Again, we are given the sample size, population standard deviation, and alpha of 0.01. Like in part B, since the alternative hypothesis is not equal to a number, in this case 35, we know that this is a two-tailed test. But here, we are given the population standard deviation, so we will calculate the Z critical value. We will input equals norm.s.inv, and don't forget for a two-tailed test for the Z critical value, we need to divide the alpha by 2 for both tails. So we input 0.01 divided by 2, and we get plus or minus 2.5758. If you're curious why we get the negative number in Excel, that is because we are calculating the Z value for the lower tail, and then we use that number for both tails since we divided the alpha in half. Let's go ahead and pull this all together and work through a practice problem. So Stone Brewing uses an automatic filling machine set so that the mean fill volume is 16 ounces for their go-to IPA machine. The machine has a known standard deviation of 0.422 ounces with a fill distribution that is normally distributed. To check if the machine is correctly filling with a mean of 16 ounces, a random sample of 49 cans was selected. The sample mean from these 49 cans was found to be 16.2 ounces. So conduct the hypothesis test at a significance level of 0.1. So the first thing we have to do looking at the story is determine if we're dealing with a one or two tail test. You want to look for language that either tells you greater than or less than. So as you can see, we don't have any language like that at all. In addition, if we think about the context filling a can at 16 ounces, we want a good machine that fills correctly. So we don't want the can overfilling or underfilling. So this implies that the hypothesis test is going to be a two-tailed test. The null hypothesis will be that the population mean is 16 ounces, and the alternative is when it doesn't equal 16 ounces. If it turns out the alternative is true, then we know we have to fix the machine. So let's find and plug in the remaining pieces of information from the story. So we were told the significance level is 0.10, and the sample of cans collected was 49. The story said the population standard deviation is known to be 0.422 ounces, and the mean ounces from the sample was 16.2. Since we're given the population standard deviation, we know we'll be calculating the Z critical value in Excel. So we will input equals norm.s.inv, and then the alpha of 0.10 divided by 2, since this is a two-tailed test, and we get a negative 1.645. We can then just plug in the values and state that the decision rule here is we will reject the null hypothesis if the calculated test statistic is greater than the critical value of 1.645 or less than the critical value of negative 1.645. Otherwise, we do not reject. So in part B, we need to find the calculated value of the test statistic. Here is the Z formula again, and we just need to plug in the values and solve. So in the numerator, we have a sampling error of 16.2 minus 16, and we get 0.2. In the denominator, we have the standard error. So we take 0.422 and divide by the square root of 49, and we get 0.0603. Then we just take the 0.2 and divide by 0.0603, and we get a Z test statistic of 3.32. Now we can draw a conclusion per the critical value method. So I like to use a visualization to help us with this conclusion. Since the Z value is way out here on our curve, we know that this is our rejection region. So since the Z of 3.32 is greater than the critical value of 1.645, we reject the null hypothesis and conclude that the population mean is not equal to 16. So the manager of Stone Brewing should have a technician inspect the machine for any issues that might be causing the machine to consistently overfill the cans. Well, that wraps up the critical value method for conducting a hypothesis test. In the next video, we'll review the p-value method.